Dimensions and points are corners in space related to binary code, Fibonacci sequence, and number of directions going in 90-degree angles to connect all points in space for a dimension in relation to primary, secondary, and tertiary colors. If I take one point in space, this would be the 0th dimension, or 2 to the 0th power for binary code. 2 to the 0th power equals 1 in space. Going to the first dimension from a point in space, we have a line for the first dimension, or 2 to the 1st for binary code. 2 to the 1st equals 2 points in space on both ends of the line. Going from the first to the second dimension is 2 to the 2nd power in binary code, or 4 points of a square on a flat plane in space. Going from second to third dimension would be 2 to the 3rd power, or 8 points in space for the corners of a third-dimensional cube. Going to the 4th dimension would be 2 to the 4th, or 16 points in space. Then going from the 4th to 5th dimension would be 32 points in space. So basically, 2 to the n number of points from the nth dimensional figure, the number that we use to multiply for 2 to the power of equals the number of dimensions. So 2 to the 1st equals 1d, 2 to the 2nd equals 2d, 2 to the 3rd equals 3d, etc. So that's a fairly simple observation to see, with the numbers or dimensions added to space in relation to how many points, corners there are in space. What is interesting also to look at is the number of directions going in straight 90-degree angles or being limited to going only in linear directions, similar to our third-dimensional world, where the 3 dimensions for length, height, and width are 90 degrees apart from each other. Therefore, we can only go in straight lines, vertically or horizontally, so one would have to go in 2 directions to reach a diagonal point, similar to the Rook in the game of chess as far as the directions the Rook is allowed to go on a flat plane in space, aka the chessboard. As I digress, going back to the dimensions in space and number of corners for each dimension, what is interesting to note is the number of directions limited to 90-degree angle turns for changing directions in space. It takes to connect all points of a dimensional cube or shape in space, and how this relates to Fibonacci sequence, you could say, with adding the numbers of directions in space for the binary code values to figure out the number of directions needed to connect all the points in space for every added dimension. For instance, going from a point to a line in space, we can only go in one direction to connect both points to the first dimension to result in our one-dimensional line that connects both points in space on both ends of a line. Now going from the first to the second dimension, one has 3 points that need to be connected to the initial starting point in space that go in 3 directions to formulate a square on a flat plane in space. The 3 directions needed to connect all 4 points in the second dimension are sideways or horizontally for the length direction or the first dimension, going vertically or up for the second dimension for height, and the third point or direction taken to connect all 4 points is actually diagonal from the initial starting point in space that requires one to move both horizontally sideways and vertically up from the starting point in space, which would be 2 directions taken for both length and height in the second dimension to reach the final third point in space for connecting all corners of a square on a flat plane in space. So one can take 2 to the 0th power plus 2 to the 1st power equals 1 plus 2 equals 3 for 3 directions to connect all points in the second dimension. This is similar to the 2 primary colors plus 1 secondary color for a sum of 3 different colors used to reach the endpoint, the final color, which would be the secondary color or sum of an equation of adding 2 colors. So one could say that the length or first dimensional direction, blue, for the first point connected to the initial starting point in space to form a line or length. The height equals yellow for the second direction or dimension for height to connect a second point. Then one could say that the diagonal point equals green or yellow plus or blue plus yellow or length plus height to connect the third point in space to result in 2 primary colors plus 1 secondary color that equals 3 different colors for 3 different points in space for the second dimension. For the third dimension, we have 7 additional points that are added or connected to the initial starting point in space, which correlates with our current spectrum or 7 rays of light. 2 to the 0th power plus 2 to the 1st power plus 2 to the 2nd power equals 1 plus 2 plus 4 equals 7 directions to connect all points of a 3D cube in space. We have the 3 primary colors that go in one direction at 90-degree angles or lines from the initial starting point. We can go sideways for length, 1D equals blue, up for height, 2D equals yellow, and we can go backwards for the width, 3D equals red, at a 90-degree angle from the starting point in space, so that correlates the three primary directions taken in the third dimension to the three primary colors blue, yellow, and red for the first three directions, out of 7 total directions needed to connect all the points of a cube in space. For the secondary colors, green, orange, and violet, one goes in 2 primary directions to connect 3 points that are diagonal to the initial starting point of the same plane at the starting point. The last or 7th point needed to connect all 8 points of a 3D cube is the diagonal point on a parallel or different plane than the starting initial point, which could represent the tertiary color or 7th point connected in a 3D cube to complete the task of connecting all points in space for the third dimensional cube with 8 total points in space. And just taking a look at this 3D cube right here. There you go. And then, of course, there is also this cube, which I use to basically connect the primary additive and subtractive colors in physics with the dimensions in space, and then binary points on a cube, along with music note lengths. Right here, as seen right here. So basically 0 equals all the colors, the 3 subtracted colors for primary colors. And then 1, 2 to the 0th power equals x plus x minus the 2 other dimensions, which is 2 to the 0th power, which equals 1, or a quarter note in space, that's x. And then y would be 2 to the 1st power, which is basically negative x plus y, which would be the equivalent of a half note, or 2 minus z, or 2 to the 1st power for the second point. The third power is quarter note plus a half note, plus x plus y minus z, which equals yellow, which would be red plus green for the physics colors being added together, or 2 to the 0th power plus 2 to the 1st power. 1 plus 2 equals 3. The fourth dimension, the fourth point, is a whole note, which is blue, which would be the last dimension plus z minus x minus y, or 2 to the 2nd power. The point 5 would be adding the first dimension plus x plus z, the whole note plus the quarter note, to equals 5, or 2 to the 0th power plus 2 to the 2nd power in binary code, which is 1 plus 4, which equals 5. 6 is a half note and the whole note added, or dimensions of x, y and z minus the first dimension x, or 2 to the 1st power plus 2 to the 2nd power, which equals 2 plus 4 equals 6. And then the 7th dimension, which adds all 3 of the physics additive colors, red, green, and blue, quarter note plus half note plus whole note, 1 plus 2 plus 4 equals 7th, or 2 to the 0th power plus 2 to the 1st power plus 2 to the 2nd power equals 7 for the points on a cube, a 3D cube.